So let's get started. So what is machine learning? Now we have already come across these terms a couple of times, and we did take a shot at defining machine learning formally in module 1. Let's take a deeper look at it. Now we are already familiar with this definition. So when we define machine learning, we define it as the art of making machines intelligent without explicit programming. Let's take a minute to understand this in a more effective way. So in general, any machines in this context can refer to a simple software program or a computer application or a product. So let's say a simple application like a chatbot, a chat system where you can fire in a couple of queries and you get appropriate responses. Now, if this chat system is supposed to be intelligent, you need to provide it some rules. So let's say you have a very minimalistic chat system where let's say you ask a question, hello, what is your name? And the chat system responds with the answer saying, hi, my name is Josh. Josh should be something which is coded inside. So what it internally does is it identifies the input that you have given. It just tries to understand how we can infer this input, where it will do some condition checks. If it finds an appropriate response, it will actually fire you with the answer. So that process could be a simple if-else loop where you're doing a simple string comparison of, okay, if the question is, hi, what is your name? You need to respond with, hi, my name is Josh. Now that's like a extremely simplistic chat-based system, almost useless, where you can just ask one question and you can just get an answer. But then let's say if you make a more complicated or a more sophisticated version of a chatbot, it could be a set of nested if-else loop. So let's say it could start with, okay, if it's an opening statement like hello and a greeting statement, the chatbot is supposed to reply with a greeting statement. If it's a question statement, like let's say, okay, what is your name? Then it needs to identify the kind of question it's asking, and it can answer 4 types of answers. So something, let's say name, age, location, and something else. And in this process, it can create a list of hierarchical rules or set of nested if-else conditions and kind of make a complicated chatbot which will give you answers to a couple of questions that you've asked him. Now, if you ask a question which is beyond the boundary of these nested if-else conditions, it's relatively going to give you no answers. So that's what you call basically intelligence. You are teaching a machine how to respond to a couple of situations in a very rule-based way. But this is not explicit programming. Sorry, this is explicit programming. What if you had a situation where you just teach the chatbot a couple of rules, and in due course of time, as in when you chat with another user, the chatbot system learns to adapt to new responses with a feedback mechanism. So let's say today, if the chatbot is answering a question and the user has indicated that it is not really happy with the answer, the chatbot will kind of learn this response and try to come up with a better response next time. So it's kind of becoming intelligent, but without explicit programming. That is, you have not coded up all the rules that you would actually expect a system to encounter. So that's in a nutshell how machine learning works. Now let's look at a formal way of understanding what machine learning would be, and then we'll go into a very layman explanation for that. So machine learning field or machine learning algorithms are basically a technique which would execute some task, improve the performance with experience E. So breaking it down, what it could be. So it could execute some task. It could be something like regression or classification. Now to make it even simpler, the task would be, okay, predicting whether it's going to be, predicting whether there's going to be rainfall tomorrow or not. Or another example would be, okay, predicting what is the score that the student will achieve in his final examinations. So that is a task. You're predicting something which could be a regression problem or a classification problem. Now it improves the performance. You would have some expectations of performance. It could be, let's say, out of 10 times, you need to be correct at least 6 times. And let's say if you're trying to predict a score, which could be something like, let's say, marks. So you would have a percentage threshold of error. Okay, this would be the error which would be acceptable, and so on. So it needs to improve the performance. And how does it do that? With experience E. which is nothing but data. So you have some data. From that data, you will create an experience, learn something, and perform a task T with some performance measure P. In a nutshell, we have three elements: task, performance, and experience. Now, this is a formal way of looking at machine learning algorithms. Let's look at a very layman approach to it. So, the machine learning process or a machine learning algorithm is similar to a 5-year-old child or any child understanding or learning new things. So, for example, let's say you are teaching uh, a 5-year-old child to distinguish between different animals. And let's say for simplicity, in the entire universe, we have only 6 to 7 species of animals. We would have cats, we would have dogs, we would have other pets like a mouse and a couple of birds, and so on. So now, out of let's say 5 simple categories, or in fact, let's make it simple. We can have cats, dogs, and birds. Out of these three different categories, you are helping a 5-year-old kid distinguish different categories. So ideally, when the next time a 5-year-old kid sees a dog, you would actually be able to predict, okay, this is a dog. And next time he sees a cat, you would say, okay, fine, this is a cat. Right? A very simplistic example to understand. So basically, what's happening is he is performing a task. That task is basically predicting which category of species or a pet he's looking at. It could be a cat, it could be a dog, or it could be a bird. And he's using some experience. He's using some experiences because you are teaching him, right? So you are actually showcasing him some examples. You might have a pet, your neighbor might have a pet, your another friend might have a pet. You're just helping him understand, okay, fine, this is a dog, this is a cat. And now this is nothing but training examples. You're providing him data to understand and learn from. And then finally, he has to perform. So he is one day given randomly, okay, a new species, a new pet, and he's asked to predict what is this. So he's using his inferential understanding. He's used whatever he's learned and he's inferencing something and creating a prediction. Saying, okay, fine, I understand based on my observations that this is a cat. He might be wrong, he might be correct. Now, if he's wrong, he needs to improve. That process has a performance metric. So in a nutshell, he's doing some task, which could be predicting a regression outcome or a classification outcome, and he's improving his performance using the data, which is experience E. That's in a very simple layman approach how we can define machine learning algorithms. Now, if we take a more deeper look, generally machine learning algorithms can be classified into two main divisions. We can have supervised machine learning algorithms and we have unsupervised machine learning algorithms. There is also room for a third category, and that's called semi-supervised algorithms. We'll talk about it, but we won't get into the depth of it. Now, before we understand the different kinds of machine learning algorithms, let's look at the process, how a machine learning algorithm is built. Now, the building an algorithm is a three-step process. We'll actually first represent it. It could be defined as an algorithm and a couple of parameters. You define an evaluation criteria, like an objective function, and then you'll find out a process to optimize it. To make this understanding a little bit easier, let me just help you understand this with a visual tool. So, any machine learning algorithm can actually be simply defined in three steps. First is the representation. Next is the evaluation. The last step would be optimization. Now, we'll simplify this by tying the understanding to the same example which we have cited over here. So, let's say you're trying to predict what would be the score of a student in the final examinations, right? That is a kind of problem that you are trying to solve. Now, how do you represent this in a form of mathematical equations? Now, let's say you are trying to solve this problem, and this is a problem which is a regression problem. So in a simple term, it could be called as a linear regression problem, right? Now, there is a way where we can formally define the parameters and the technique in a mathematical way. So this could be defined as, let's say, y is equal to mx plus c, right? So y would be your dependent variable, which is, let's say, the score. X would be, let's say, one attribute, like, let's say, the number of hours a student has studied for. M would be the coefficient. Now, this coefficient is the parameter, and C would be a intercept, or basically the unexplainable part of variance. Now, this is, let's say, the mathematical equation which we want to represent for a problem. Now, when we evaluate, what would we evaluate? We would evaluate for an objective function. An objective function, in simple terms, can be the way you understand how your model is performing. So let's say for this particular equation, you identify a way to find the parameters n. Now, how do you understand whether this value for m is good or not? That's when you have the objective function. Now, the objective function, let's say for linear regression, can be defined as, so let's say the output is y, and you have predicted y dash. And the difference between the two could be y minus y dash. And if you do a simple construction of percentage, let's say y minus y dash upon y into 100, you get the percentage error, right? Now, how would you define this as an evaluation criteria? You would say that your evaluation criteria needs to have the lowest percentage error. So you would have this equation in front of you, y is equal to mx plus c. Now you've represented that. Now you need to evaluate a criteria, and that criteria is percentage error, which means that at any point of time, you'll try to have the least percentage error. So in iteration 1, you did some math and you computed something and you got, let's say, 25% error. The next step would ideally try to reduce this to, let's say, 15% error or any number. And at the end, it will try to take the least possible value, where you'll have a scenario where you have the minimum amount of error for that equation. Now, this process of improving the value from one value to a lower value, let's say from a higher percentage of error to a lower percentage of error, is the process of optimization. Now, how do you mathematically approach this? They have a lot of different fancy names, and we'll get into the details of those techniques in a while. So in a nutshell, we first represent the algorithm or represent the problem. It could be represented as a linear regression algorithm, where we have the equation y is equal to mx plus c, or it could be represented as a different classification problem, where we would have a different algorithm for that. So the representation will also change. Now, this being a linear regression problem, what would be the evaluation criteria, which is the objective function? The objective function, in a nutshell, could be something that we're trying to understand how is the model looking like, or how good are the parameters. Now, we just divide one rudimentary approach over here, which is percentage error. There are a lot of better ones, but then this is just for basic understanding. So we're saying, okay, fine, the objective function or the evaluation criteria is percentage of error. The percentage of error should be the lowest. And the process of improving this percentage of error so that you get the best values for your parameter, y is equal to mx plus c, where m is your parameter, is the process of optimizations. And you have various techniques to go through optimizations, right? So that's how you can represent or build machine learning algorithms in 3 simple steps. Let's get back to the details. What are the different kinds of machine learning algorithms? So as we already discussed, we have two major types: supervised machine learning, unsupervised machine learning. And we'll get into the details of semi-supervised learning, which is not mentioned over here in a while. So supervised machine learning is a scenario where training is done using labeled data. Now, what do you mean by labeled data? Labeled data is a scenario where you have the actual values for a problem. So coming back to the same problem, let's say you're trying to predict what is the score that will be obtained by a student in his final examination, right? So for this scenario, assume that you have a class of 100 students, and out of those 100 students, you have around 60 students for whom you have recorded some sort of metrics or some sort of data. Now in this data, you'll have, okay, historically, 60 students have studied for, let's say, 40 hours, and their equivalent score was around, let's say, 85%, or whatever GPA you would actually consider for that. So you have data for for let's say 60 students. For these 60 students, you have data where how many hours have they actually invested in study and what is the score they obtained. So we have 60 different records. And in each of these records, we have the actual outcome. So we have the input data, which is let's say the number of hours he studied for, and we also have the outcome data. Now this is the data the algorithm will use to learn. So it will learn, okay, fine, whenever let's say there was 80 hours of studies invested, the equivalent score was let's say 95%. Somebody studied for 45 hours and he scored somewhere around 65, and vice versa, so many more combinations. This is a scenario where we have the actual data, right? And the algorithm, as I already told you, learns the mapping function from the input to the output. The most simple example would be regression, like I just mentioned, when you're trying to predict whether a student, what is the score that the student will obtain in his final examination. Or it could be a case of classification. Let's say you're predicting a categorical value. The categorical value would be something like, let's say, whether a student will pass or fail. So, for the same example, if you just do a simple modification. So, let's say you have the number of hours a student has studied for a semester examination, and you have the result of that student, whether he is passed or failed. So, a student who has invested 60 hours of studies has passed. Another student who has devoted 50 hours of studies has also passed. But another student who has studied for only 20 hours has failed. You have this data, you learn from this data, and then later on you can predict for a test data where you don't have the outcome. So once you've learned the mapping, you can leverage this data to predict what would be the scenario if the student would have studied for 80 hours. Now using the mapping, you can actually predict, okay, fine, if the student has studied for 80 hours, using the mapping function algorithm I have, I understand that he would mostly pass. That's an outcome. So that's supervised machine learning algorithms. The difference over here is you have training data which is labeled. On the contrary side, you have unsupervised machine learning algorithms. Now, this class of algorithms do not have labeled data. So the training is done using unlabeled data. So what would be unlabeled data? You have a bunch of students for whom you have different attributes. You would have attributes like the number of hours you studied in, the gender, age, probably height and weight, and a couple of descriptive attributes. But then you don't really have an outcome variable, let's say something like whether the student has passed or failed, or the kind of score he has obtained in an examination. Now, what are the different use cases that we would solve in this scenario? One example would be clustering. So clustering is basically used to discover inherent groupings in the data. Now, in unsupervised learning algorithms are left to their own to devise and discover patterns present in the structure of data. It's going to mine the data and understand, okay, fine, these are the patterns I find in the data, and based on these patterns, out of these 100 data points, I find 60 of them are close to each other, another 10 are close to each other, and the remaining 30 are close to each other. So I can form around 3 different groups of 60 members, 10 members, and another 30 members. That's clustering. You basically uh, use the data to understand inherent groupings in the data. And this is done without the label. You don't really have an outcome that this is just what happened to these students. And then similar to that, we have association rules. Association rules are used to discover rules that describe large portions of data. So for a traditional example, let's say you have data from a retail store, and this data is transactional data. So a transaction would be like you would have bought milk, bread, eggs, and let's say chocolates. Another transaction is where a person has only bought milk. Another transaction where a person has bought milk and chocolate, and let's say honey. So you would say an association saying that whenever you buy bread, there's a very high chance that the person will also buy eggs, because you see an association between bread and egg. So whenever out of 100 times when a person has bought bread, 75 times he's also brought eggs. That's an association you're trying to define. So this is the way you actually understand and discover rules that describe large portions of the data. You basically create associations. And this is the most common way of trying to understand like how we can upsell or cross-sell a customer. So customers come to the store, has bought honey and ginger. You might recommend them, okay, why don't you buy lemon? Most of the guys who have actually bought honey and lemon have also bought ginger, or vice versa. So that's unsupervised machine learning algorithms. Now, the third category, semi-supervised machine learning algorithms, is something which we have not showcased over here. So I'll just give you a brief introduction over there, but then that's not something like which we would keep that out of the scope for this course. It's a very relatively simple topic and used in only special scenarios. Semi-supervised is a combination of supervised and unsupervised. Now, the most layman example would be you would have some data which is labeled and the remaining data would be unlabeled. In a nutshell, you could actually leverage the supervised algorithms from the labeled data to create an algorithm and predict for the unlabeled data. So let's say for 100 students, you have 60 students who have, for whom you have the number of hours studied, and you have the kind of outcome whether they have passed or failed. Now you leverage this labeled data, create a supervised training algorithm, and then predict the outcomes for the remaining 40 and create labeled data. So that's semi-supervised. You use a bit of supervised machine learning algorithms to predict the remaining labeled data for the ones where you don't have labels. That's a basic introduction to machine learning. We've just understood a basic definition, which is like making machines intelligent without explicit programming. We took a formal way of defining how machine learning algorithms can be defined in terms of three parameters: task, performance, and experience. We looked at a three-step process to build machine learning algorithms, which could be defined as representation, evaluation, and optimization. And we looked into the two classes of machine learning algorithms. We have supervised machine learning algorithms and we have unsupervised machine learning algorithms. And we also acknowledge the fact that there is a third category, which is semi-supervised. Now, in reality, supervised machine learning algorithms are the most popular and widely used class of algorithms. In general, most of the machine learning techniques that you would see getting deployed in the industry or being used in any scenario will mostly belong to supervised machine learning algorithms. There's wide acceptance for supervised machine learning algorithms, and relatively, unsupervised is probably second. I mean, you definitely have tangible use cases where unsupervised machine learning techniques are on the front, but then supervised machine learning algorithms takes away the glamour. Let's move on to understand supervised machine learning algorithms in more depth.